All right, it's time to review the code for this Arduino-based torch height controller I made for my CNC plasma cutter. Now, if you haven't seen the other videos I've done already, I'd recommend you go back and watch those first. In particular, this one covering the PCB, the wiring diagram, and how the hardware in general works. And there's another one demoing this THC running on my plasma table. So if you haven't seen them, I'll put links to them down in the description below. They're also included in the overall CNC build playlist, which again is linked down below. Now the code, as you see it here, is the latest version of the code. It's what's running on my THC, and it works just fine. So this is already up on GitHub, and I'll have a permalink to this exact version of the code, once again, down below. I don't foresee making any changes to it in the nearby future, but over the longer term, if there are any more updates or changes to it, then those will be available in the latest version of the Git repository. So if you go on GitHub, check out the latest version of the repo, you can see what changes have happened to this file since the time of me shooting and publishing this video. Overall, I don't see there being very much, but that's the beauty of Git. You can always go back and see the old stuff versus the new stuff and see what changed when and hopefully why. Now with that out of the way, let's get into it. So this here is an Arduino project, which means it's basically some light duty C code. You know, it's a little bit techy, I'm not gonna lie, but it's also not that bad, okay? It's not that crazy. I think I wrote this pretty well. I've put, pretty good comments in here. So with this and the overview we're doing now, you should be able to follow along, see the parts that you might need to change to make it work for your setup, and kind of understand what each bit's doing in case you want to make bigger changes to it overall to really customize it for what you're doing. Now again, this is an Arduino project, but I'll point out we're not looking at it in the Arduino IDE right now. Personally, I can't stand the Arduino IDE, that white and blue awful text editor. I think it's awful, ugly, slow, just all sorts of bad, and Java based. But that's just me because I'm a software engineer and kind of picky on those things. So we're looking at this in a basic text editor, but the file and everything is overall the same. All right. And personally, when you'll be using this code, you're probably running it in the Arduino IDE, and that's totally fine. Now, as long as you've done some basic Arduino stuff before, walking through tutorials on either the Arduino project website or on Adafruit or SparkFun or any of those other really great, Arduino and, basic circuit board tutorial sites, then you should be able to follow along with what we're doing here. The main thing to remember is I wrote this to be a very naive and very fast program, okay? And the reason for that is the signal that we read off the plasma cutter is very spazzy. There's just a lot of noise off that torch arc voltage, okay? It goes just all over the place because plasma cutters in general are just noisy things. So I found the best way to get a fast and consistent response out of this THC is to sample the plasma voltage as absolutely fast as possible, do a little bit of smoothing on that, and then continually relay up and down signals back to LinuxCNC, and the kinematics engine of LinuxCNC figure it out from there. Okay, so this THC is basically shouting at Linux, going like up, down, up, down, up, 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 down, 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 up, 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 down, down, back and forth over and over again at a couple thousand times per second. And LinuxCNC can then take that, calculate where the torch currently is, where it's supposed to be, and how fast it needs to move to get there. So while we're sending a bunch of signals that are relaying a bunch of that noise to Linux, once it gets to Linux, the kinematics engine kind of cancels it out. So that's what ended up working well for me. We can run over some tests and things later. If you want to try changing this code, you're more than welcome to experiment and see what works better on your setup. But to kind of explain better why I need this thing to operate quickly, let's imagine you're cutting some very thin sheet metal, right? You cut thin metal at maybe up to 180 IPM, right? That's a pretty good clip. So what, 3 inches per second of X and Y travel. And a plate that thin, you're probably about 30 thou above the plate, skating just over the plate with your torch head. So if you're moving at 3 inches per second and you're 30 thou above the plate, if your plate has a 1% slope to it, then if your THC can't respond basically immediately, within the course of a second, you can already be dragging your torch along the plate. Okay, and you don't want that. So by having the THC respond quickly and not including too much low-pass filtering in the hardware or too much smoothing in the software here, we can make it respond fast, and again, let LinuxCNC and the kinematics engine figure it out from there. So the code begins up here with this boilerplate for the 7-segment LCD I'm using. You know, that brain-dead common cathode LCD we discussed at length in the last video. So for those styles of displays, you use the sevseg library, which you can get up on GitHub, and it's basically just plugging the pins that it uses and then calling the API functions as in the examples for that library. You know, it's very, very basic. If you're using a different kind of LCD, then follow the tutorial for the LCD you're using, and you might need to change bits of code. We're referring to this sevseg here. But you know, if you can get the example for whatever display you're using to work, then you can make that same thing work in the code here. Now the pin values that I've chosen all match up to what's shown on that wiring diagram we covered in the last video. The numbers here are kind of all over the place, but that's just because that's the way I had to lay them out to make it fit cleanly on the physical PCB. You know, this is digital pin, 12, 10, 9, 2, and it seems kind of random, but it flows nicely when you're wiring the traces from that LCD to the Arduino Nano. Again, if you're doing your PCB with an Arduino, Mega or some other thing, you got to redo the wiring there. You might need to change all this, but as long as you get the pins, lined up with what you have it physically set to do, then it should work. Next up, we're defining a scaling value for the analog pin that we're reading the plasma torch from. So down in our looping function, we read an analog pin every time you get the plasma arc voltage. But those analog read functions for an Arduino return a value between 0 and 1023. Right? They don't give you a voltage. And if you've read any of the basic analog tutorials for Arduinos, you should be familiar with that already. So the ADC gives you a value between 0 and 1023. To scale that to a voltage, we divide that by 1023 and multiply it here by the reference voltage of our ADC. Once again, in that PCB video, we covered that I'm using an external voltage reference. I have that LM317 set up to give a very precise, very consistent voltage to the Arduino so it can also get consistent and even measurements. So mine is giving out a value of 4.45 volts, so we can get that to the same 4.45 volt scale by dividing by 1023 and multiplying by that AREF, and then we multiply by 50 because the plasma torch itself has a 50-to-1 divider already built in. So that ends up giving us a value of about 0.2, and if you multiply whatever the analog read function returns by 0.2, that will give us a reading in straight up volts for the plasma arc. Now, as I discussed last time, again, because this, 4.45 times 50 really only gives us a maximum value of about, 220 volts, right? If we go above that, we're going to see clipping in the values of reading. But that's okay because the typical operating range for my plasma cutter is between 100 and 150 volts. The Hypertherm PowerMax D5 I've got can return arc voltages up to 300 volts. But when it's running, it should really be in the range of 100 to 150. So if we ever end up maxing out the ADC and it's just returning solid, 1023, 1023, 1023 every time we read it, that means the arc voltage is somewhere either at 220 volts or above, and that simply means the plasma torch is way too damn high, and we have to lower the plasma torch ASAP. So clipping at the top end shouldn't really matter. Now when it comes to your own setup, depending on what your external reference is for your ADC, you're probably going to change this volt value right here. And then depending on if your plasma cutter has that divider or not, and what the divider is, you probably also need to change this bit. But, again, this is explained pretty well, and just plug in the numbers that you need for your setup. Next up, we're defining a threshold for when we tell LinuxCNC to either move up or down. Because these values are a little bit spazzy, we don't necessarily tell LinuxCNC to move up and down when it's reading close to the target, right? So down later on in the loop function we'll get to, we calculate how far our current reading is off target. Okay, we'll get to this more a bit later. We calculate how far we have to target, and only when we are either above the threshold or below the threshold do we send the signals for up and down. And otherwise, we just say, stay where you are, you're close enough. So if we're reading like 120.2 volts and our set point is 120, we don't bother telling it to move because it's close enough already. Let it rest for a second. But once it starts reading, 122, 125, or 115, then we start sending up and down move signals. So the threshold value here is in terms of ADC counts, again on that 0 to 1023 scale. So if you want to think about what this is in volts, you'd be multiplying that by scale. So a thresh of 5 when your scale is 0.2 means that you are using a threshold of 1 volt. Another thing I want to point out about the calculation for the scale here is that if you're not familiar with a define macro in C programming, this is basically saying wherever the phrase scale appears in the code, replace it with this literal value, with this full calculation here. And again, wherever thresh appears, replace it with the literal value of 5. Now when we have something like this, where it's doing some arithmetic, luckily for us, once this compiles and gets ready for uploading on the Arduino itself, this value has already been calculated out everywhere we use it. So you could also do, define scale as the 0.2174 or whatever. You can also do that exactly there. But this is no faster than this. So the exact same speed, they end up being the exact same thing on the Arduino. So personally, the code, I write it out because it's a bit more easy to follow along with what is going on. All right, next up, we're setting more macros for the minimum maximum values on the knob that we use to set the set point when the Arduino starts up. Next up, more straightforward stuff. We're just naming the pins that we use for other parts of the plasma cutter. All these digital pins basically get eaten up by the LCD, and there's a few analog pins we use, both for reading the adjustment knob for the set point, the plasma arc voltage, and then these other 2 pins we use for setting the up and down signals to LinuxCNC. Once again, different Arduinos have different restrictions on what analog pins can be used for writing digital output values, but on Arduino Nano, A2 and A3 do work for digital output, down here in the looping function. So once again, if you're using a different Arduino, you might need to change these pins around, both in the wiring on your physical board, and then also here in the code. So next up, this whole block kind of works together. Like I mentioned, we want to do some smoothing of our reads here in the Arduino software. Not too much, but a little bit. And the way I'm doing that is with a circular buffer. So over in Wikipedia, take a quick look at this article, and it kind of explains the concept to you of you have an array, and you basically go along and fill that with values. Every time you do a read, you have 1, then you add 2, 3, and you keep going. And when you hit the end of your buffer and you kind of filled up as many values as you want, you go back to the beginning, begin writing over there, and eventually you cycle around all the way and begin overwriting the old stuff with new stuff. So in the code, we are defining this array right here of integer values, and we're giving it up to buff size slots to fill. So 512, it's just a oversized array that we can fill with values to do our averaging. Now I tested things up to 512, and in the end I found that again the shorter moving averages work the best. So we're going to use 16 for this. You can try other values to see if that gives your plasma torch a better or worse response. But I found in that very short moving window in the average worked the best. Now there's a second moving average we're doing that I guess that one we'll talk about a little bit more later. Yeah, we'll save that one for later. But for now, remember we have this array here called values, and right now we're just filling it up with zeros. But later we're going to put ADC reads in there, and then cycle back and overwrite them as you read new things, so you can keep track of the last 16 reads. Okay. Beneath that, we're defining a few more variables for generic use. We got one to hold the differences that we're reading for the arc voltage, one to keep track of the mode over here, whether it's saying move up, move down, or stay where you are. We've got a few more temporary values used to just chuck things that we're reading, things are doing some loops, and that's the stuff for keeping track of the time on startup. Next up, we got the setup function, which is the basically the initializer for your Arduino. Right, this whole setup function runs once and exactly once, and then it doesn't run again. And the main thing we're doing in here is reading the adjustment knob to set the set point for the plasma cutter. And we only do that once in the setup because by not letting you change the set point once the Arduino has already begun reading values off the plasma cutter, we can save that second analog read every time. Okay, so basically, the Arduino ADC can read about 9,000 samples per second if all you're doing is reading ADC values. This code, as tested, can get between 6,000 and 7,000 samples per second. It's pretty good. It maintains almost all the speed of the original Arduino ADC. Even though we've added all this extra code, it's pretty well optimized. But if we were reading both the set point pin and the plasma pin on every loop, that would end up cutting effectively the number of plasma reads you can get by half. So we only read that set point during the setup function, and then we lock it in for the rest of the torch's operation. And then to adjust the set point, you hit the reset button on your Arduino, then you tweak it. Okay, it's a little bit of a hack, but it does make it work overall better. So, beginning at the top of the setup function, we just explicitly set a couple of the pins we're using here. Then we set the analog reference to be that external 4.450 volts we're applying. Basically, this external value here, this is one of those magic Arduino provided things. You tell it external, and it knows that it's going to read that AREF pin to get the reference for the ADC. And according to the Arduino docs, you need to read a few analog values after setting an external reference just to help make sure the ADC has stabilized and gotten that voltage accurately applied. So I just told it, read it 5 times, check those values away, but just read them just to make sure the ADC is stabilized. Next up, we're going to be doing some fancy math here that we'll get to a bit more because this here has to do with those moving averages on the plasma reads. Not important right now. Next up, we're doing some setup for that sevseg thing, right? Just telling it, we have a common cathode, number of digits, all that jazz that we already set the variables for up above. As for the brightness, that's just some integer value you pass, and you might need to tweak that for your specific LCD so that it's visible but not blindingly bright. In my case, I found 50 works pretty well. Your mileage may vary. Next up, I'm setting that to a very basic, just the string A8C0. And why? Well, because that string looks kind of like ABCD in all caps. And it's just a simple thing you can see to be able to tell when the Arduino resets, right? So if you hit that reset button and you don't have it put out something noticeable at first, you might not be able to tell whether the button press really took or not, if you manage to hit the button and make it actually reset. So by just displaying that on startup, it's like saying, when you start your Windows computer and it says like, welcome to Windows or whatever the hell, it's the same idea. It just says like, I've reset, just FYI. And then we make that run and display for half a second. Now, one funny thing about these 7-segment LCDs is that in order for them to display a value, you have to keep calling this refresh display function. So rather than having it, set the characters and then sleep for 500, I have it loop 500 times, refreshing the display over and over, and then delaying for a millisecond on every loop. Bit hacky, but that's, again, like I said, these LCDs are the most brain dead type. If you got a fancier one, you might do that differently. Just have to display once or whatever. But for this, that's how you make it work. Next up, we get on to the part where we're actually setting that set point. So we start off by resetting our loop counter that we just used up here. We keep track of the current time, and we calculate what 5 seconds later is. So the way I have this set up is when you change your set point, it will let you go for another minimum of 2 seconds longer. So as long as you keep turning the knob, you can keep on turning the knob until you dial it in just where you want it. But after those 2 seconds pass, then it locks in. But there's a minimum here of 5 seconds of adjustment time. So it gives you, a bit of time to work as you want to, set that value locked in. So basically, while the current time is less than our time limit, we read that pin. And now here's where we get using the circular buffer for the first time. So we have this value that we just read, and now we're going to keep track of all the reads we've done, right? So our total is equal to the read we just did, plus our last value of total minus the oldest read. Okay, this might be a little bit complicated. Let me try and explain, right? So if we got this buffer, and currently on the first loop, I is 0. So our total is also 0. So then our total equals that temp value we just read. That one thing we read, boom. And then next time we loop through, we'll have stored that value in our circular buffer in the first slot, which is indexed slot 0. Because in C, when you have one of these arrays, you start counting them. This is 0, this is 1, this is 2, all the way up to slot 511 in our case, because we set buff size up above to be 512. All right, again, if you have questions, ask below. I'll try and help. And Arduino tutorials, again, on SparkFun, Adafruit, and the Arduino Project website will help get you a feel for some of the C code stuff. But yeah, so we keep track of the total by continually adding the current thing we read, and then subtracting the oldest value, and then saving the current value we read in the place of what the oldest value was. And if we keep track of the total for a certain number of reads, and then divide by that number of reads, it gives us the average. And then the average is our target. Okay? Again, I know, yeah, a little bit fancy. Squint at it, turn your head to the side, look, maybe have a beer or a coffee, whatever, until it makes sense. And once we have this target value, that's telling us, again, on this 0 to 1023 scale, what is our potentiometer reading, okay? But we need to convert that to the voltage set point we want to use. And that's where we end up doing this down here. We're taking our minimum value and then adding to that, basically scaling our target according to your 1023 ADC range times the basically the total difference in the max and the min values of your set point. So we calculate the voltage we're using, and then to chop it off to a single decimal, a trick you can use in C is just multiply by 10 and then divide by 10, and that will, if you cast it to an integer value, it will lop off all the extra digits. Just because, it's a bit easier for the Arduino to not have to keep track of all those extra digits, I guess. Floating point decimal math on Arduinos is better to be avoided if possible. So we keep track of that for the display, but when we are actually keeping track of the target we're using, we do that in integer ADC counts later on. But anyway, once we've calculated the set point based on our current average, we say if that's different from what it just was, then we overwrite what the new value is. We set our time limit to be either the current limit or 2 seconds later in the future. Using this max here means that we get the minimum of 5 seconds, but possibly up to 2 seconds longer. And then we adjust the number displayed by the sevseg library. And then we increment the counter value and have it loop back around every 10. So in C, this operator here is called a modulo, and it basically returns the remainder from division. Okay, so remember back in probably 3rd or 4th grade, you learned long division, right? And you didn't learn fractions at first, right? When you first learn long division, they teach you like, 20 divided by 6 is 3 with a remainder of 2. And the modulo returns that remainder of 2. So here if we have this counter, I, that we're increasing on every iteration of this while loop, then once I hits 10, 10 divided by 10 is 1 with the remainder of 0. And then it reassigns 0 back to I. So basically it loops forward, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And it keeps looping that way for as long as you are adjusting the knob. Then we get the current time, again, refresh our display, so you need to do that. And it just loops over and over again until you are no longer changing the current set point and you have gotten past your time limit, right? So once you're no longer changing the set point, you stop increasing the time limit, and then eventually it expires, and then you break out of this while loop. So next up, we got to convert the value we read off that potentiometer to the same scale that we're using for the plasma torch. So that potentiometer, because it's reading between ground and the A ref voltage on our PCB, as shown in the last video, it will return anything in that full 0 to 1023 range. And that's supposed to correspond to something in the 110 to 150 volt range. So to make that translation to what our plasma cutter is going to return, we need to divide that value we picked, say 120 volts or whatever, by our scale. And that will give us the ADC count value we're looking for when we do our plasma reads next up. Okay? Again, questions asked below. Okay? I hope I'm explaining this well enough though. Again, I am a software developer, so I'm not terribly used to explaining these things to non-software people. I guess funny thing I've maybe said in other videos or talked about with friends is when it comes to stuff like CNC laser cutters, all of those things have tons and tons of great software written for them, But CNC plasmas don't at all. Yeah, and I realized why this is a while ago. It's because nerds buy CNC lasers, and nerds write software. Whereas welders get CNC plasmas, and welders generally don't write software. I'm like the one exception to the rule. So hopefully, you can all follow along with this. And again, if not, that's why I'm making the video, because I'm here trying to help you guys out. But by the time we reach the end here, we basically just want to overwrite that whole buffer that we had back to be full of zeros, because we're done reading the potentiometer, and now we want to get it basically clean slate for reading the plasma voltages as we get to the looping function. And then reset the counting variables again and the totals that we're keeping track of. So down here in the loop function is on basically this loop function calls itself over and over and over again. So rather than having a while loop like we have right here, the loop function itself is the loop. Okay, it just repeats on its own. So we don't need that loop in here because Arduinos are basically set to do that by default just over and over again. So we read the pin for the plasma, and then similar to how we're doing the potentiometer reading back up here, we're saying the total is our past total plus the past read, plus our most current read, minus the oldest value that we're now phasing out. And then we overwrite that value that we're phasing out in our circular buffer. The real fancy part, okay, the most complicated part of what we're doing here is this little bit of black magic. And this is basically a fast way of doing an average. So back up here, we did the average by taking the total and dividing by 10, because we're doing 10 samples in that moving average. Over here, we're doing what's called a bit shift. And basically a bit shift is like fast division, but only by values of 2. So if you know anything about binary, If you don't, you should read the Wikipedia article on binary, because it'll help you, understand this. But in binary, you got a number like, let's say 5. So 5 would be written out like that, right? And the number, let's see, 8 would be like that, okay? So the idea of having a rightward shift is, say if you had 8 shift 1, it takes this value here and then kind of pushes everything to the right by 1. So then this last digit gets dropped. And then that means now in binary, this is 4. So 8 right shift by 1 gives you 4. It ends up being like division by a power of 2. Right shifting by 1 is 2 to the first power, which is 2. So it's basically 8 divided by 2 is 4. Now the reason why we're using bit shifts here is because these are very, very fast. And division on an Arduino is very slow. So the way we can get 7,000 samples per second is by using tricks like this bit shift, and then later on using this binary AND operator. So rather than using the modulo we use here, we use a binary AND, which again we'll discuss a bit later. But for kind of a better explanation of why we're doing this fancy black magic, basically when I did this basically modulo arithmetic with the modulo operator, that cut the samples per second down from 7,000 to about 3,500. So those two little changes of that modulo operator not or looping function make a difference of a whole factor of 2 in speed of this code. That is how bad divisions and modulos are on Arduinos. Like if someone asks you to divide things, like division is hard, right? Addition is easy, multiplication is a little bit harder, but division for people is probably the hardest arithmetic operation to do. What does Wikipedia say? There we go, bitwise operation. And then here they got the bit shifts, and they give you another example of when you're either shifting left or shifting right. So a left shift is basically multiplying by powers of 2, and a right shift is dividing by powers of 2. So way back up here, when we defined our sample size for the plasma arc voltage readings, I say here in the comment, this needs to be a power of 2 and no larger than buff size. That's why. So 16 is, 2 to the 4. And then in that setup function, the little bit we skipped over here is determining what power of 2 that sample value is. So basically we have the binary 1. So for this example, I'm going to use this as a scratch pad. 1 in binary is written like 1, right? And our shift value has already been initialized to 0 up here, right? So on the first loop here, we're saying 1 left shifted by 0 bits. It's still 1, and that's not the sample value yet. So then we increase our shift to 1. If we bit shift 1 to the left by 1, we end up getting 1, 0, because a left bit shift feeds in zeros from the right-hand side. And in binary, 10 is 2. Actually, there's a funny joke if you haven't heard it. There are 10 kinds of people in the world. Those who know binary and those who don't. And that's where this joke comes from. Yeah. Anyway, but this is still not 16, because 16 in binary is what? Let's see, 1, 2, 4, 8. Yeah, this is 16 in binary. So we haven't gotten there yet. So we're going to say then increase shift to 2, do it again. Still not there. 3, still not there. And then 4, boom. This is now when 1 bit shift by 4 is equal to our sample. And then we break out of this loop and we know we're going to be shifting by 4 bits when we do the average. So rather than doing a division by 10 like we're doing here, we're doing a fancy division by 16 by doing a rightward bit shift by 4. Okay? Oh God, I hope this is making sense. Shit. Anyway, so we have a total. Right? We have this running total that we keep track of by adding the latest read and subtracting the oldest read we're phasing out. And then we divide by 16 to get our average of these last 16 readings. And then we can subtract our target, and that gives us basically how far we are off the target, our difference. And let me delete this extra shit. There we go. And now we're going to go through and compare our difference to the threshold. So if we're reading high, say we set our arc voltage to be 120. That's going to be a target of about, 600 in terms of ADC counts. So if our total averaged out is 610, then difference is going to be 610 minus 600, that's 10. That is higher than the threshold. So if we are not currently in the mode where we're sending down signals, then we send down signals. And that's where this mode variable that we saw before comes into play. Basically, where I only set the digital write pins here if you're not currently in that mode already. So if you've already set the digital pins to say down, and then the next time you loop through, it's still down, this if mode is not equal to basically means we can skip it because we've already done the digital writes. And I've done some testing and found that this does make it run still a little bit faster. So that's what this whole mode thing is all about. So if our difference is high, higher than the threshold, and we haven't already set these pins, we set the up pin to 0 and the down pin to 1. So what this ends up doing is it connects that optocoupler from the PCB, right? Setting a digital write to 1 basically puts voltage out on that pin. So our optocoupler then lights up the LED, and then the far end with the photo transistor can receive that and make the connection isolated from the PCB on the LinuxCNC side. Okay. Again, if you haven't watched the PCB video, you're not going to get what I'm talking about here. So that's how this signal gets relayed to LinuxCNC. It's a isolated signal that then makes a connection on the LinuxCNC side. And in my case, I have this grounding a pin on the parallel port breakout board, which becomes important in the HAL configurations that we're going to start covering next. Because yes, there's another level of software stuff here that you run on the CNC controller itself. That's all the HAL files, and that's how you do all the cool shit, like adding, I don't know, I have like ohmic sensing, the THC now, a laser, zero offset for the plasma, all the cool stuff when you want to customize it a lot. That's what you do in HAL, and that's what's coming up in the next video. So back to here, imagine if our target again is 120 volts, which is about 600 in terms of ADC counts, and our total averages out to 590 instead. So our plasma is low. Then difference will give us -10, and then it ends up being below negative thresh, right? Because thresh is 5, so it's below, -10 is less than -5. And then we end up writing the up pin, right? And saying the up signal is now activated and the down signal is deactivated. And in all these cases, I'm doing the deactivation first, just so we're never sending an up and down signal to LinuxCNC at the same time, because that wouldn't make sense. And then if the difference is, less than thresh, either it's like between -5 and 5, then we simply say both of these are deactivated. And then down here, let's see. This is for the display, which we'll cover next. We're refreshing the LCD on every loop, because again, these common cathode LCDs require continual refreshing. And then we're doing the modulo arithmetic with I. So, like I said here, this is faster than modular arithmetic, but what exactly is going on here? Well, that's where we get into bitwise ands. So, I guess that's another example. If you've got a number like 5, right, that is this in binary. Now, say you have 4 in binary. Not that. 4. There we go. If you take 5 and 4 in C, What that does is it lines these two up and says where both these digits lining up are 1, we keep that. And where they aren't both 1, we make it into a 0. So if we AND these, we get 1, 0, 0. Because this 0 makes this one not follow through. These are already both 0, and then these two are both 1, so we get a 1. So then 5 and 4 gives you the 4. Okay? Now what we're doing here is we've got this samp value from which we've already subtracted 1. So if 16 is written like that in binary, then 15 is this. Okay? So what we're doing is as we increment I every time, I goes 0, 1, 2, 3, and all those values fit within this mask. Okay, this binary mask here of all ones, all those fit within there until I is 15, right? So then when I is 15, you have 0, 1, 1, 1, 1. You increment it up again by 1, and then suddenly I is 16. So when you take that 16 and 15, what you end up getting as a result is 0, 0, 0, 0, 0 across the board. And that ends up resetting I back to 0. It's like that modular arithmetic from before, but it's special and fast for powers of 2, which again is why when we have the samp value we set way up here, it has to be a power of 2. And as I mentioned here, yeah, if you do this modular arithmetic instead, that drops you down by like half the speed. So that's why we're doing bitwise shifting. Again, the article here in Wikipedia will help explain that to you. Maybe in a bit too programming terms, but again, there's also Stack Overflow as another great programming resource. Any answers you see on there. In fact, I'm sure if I just search bitwise and C, what's the first answer for? I'm sure Stack Overflow appears here somewhere. Yep, there we go. See, Arduino bitwise operations. Yeah, already there's Stack Overflow answers. If you ever got programming questions too, Stack Overflow, oh my God, there's basically an entire software engineer's job is a combination of Google and then reading things off Stack Overflow. It's, yeah, anyway, yeah. People think software engineering jobs are like, yeah, they're not all the crap. Anyway, yeah, enough of that. Yeah, so that's how we're looping over that I. And as long as samp is a power of 2 and less than 512, the buffer size, this should work. And one thing I didn't mention is the buffer size here is 512 because that lets me, test different, different sizes for that average. But 512 is also the largest power of 2 you can fit in Arduino Nano. If you try to do 1023, the Arduino doesn't have enough memory to hold that array. So I made 512 because 512 is the biggest I can fit on Arduino Nano. Then we're going to talk about the bit with the display changing, right? Because you see I got the looping for I and J here. What's that all about? And what was this display thing up here? Well, display is a slower moving average I'm keeping track of, basically just for changing display on the LCD. Because this sample, right, this moving average of 16 samples is still pretty noisy. And if you display that on the LCD, it ends up jumping around all over the place, and it's really difficult to follow what you're really getting. Again, LinuxCNC is smart enough to be able to cancel out those up and downs and all that noise. But for you visually reading the LCD, it's not so easy to tell what's going on. So if we do a slower average of, 1,024 values, that's 2 to the power of 10. That is enough that, let's see, that's enough that it makes it more stable for us to read, but we can still move quickly because the values we're basing our signals off of are moving much faster than that. So it doesn't hurt our ability to respond quickly, but it does make it easier for us to see that the THC is operating roughly how we expect. So for those display values, basically, I'm not doing the circular buffer right? Because a moving average of 1024 values is more than can fit in this 512 integer buffer. So instead what I'm doing is I'm just keeping a running tally of it. So where is that happening? Loop function, there we go. I was looking at the wrong function. Anyway, okay, yeah, so here we are. So this display value is keeping a running total of just what we're using for display. It's a non-rolling sum, just for the lower sample rate display. So every read we do, we tack that on there. And then every 1024 calls of this loop function, the j integer rolls back around to 0. And when j becomes 0, this if statement here executes. And then what that does is it does a single slow division average, right? So this divide here is technically not ideal because, again, division is slower than the bit shifting when you're dealing with powers of twos, but it's still fast enough for this thing that we execute once every 1,000 loops. So we divide our total of the past 1024 values by 1024 to get the average. We multiply by our scale to put it into voltage units that we can personally relate to. And then we reset that display total back to 0. And then that gives us a smoother thing to read on the LCD and make sure stuff works as we expect it does. Whew, okay, I think that is everything. I hope between this and the PCB, this makes good enough sense. And again, if not, always do ask questions. I'll try and help you out. I would really like to see some other people put this together. That would make me personally very happy to see the work I put into this actually come to fruition for somebody else. And then if we can get enough people to put these things together and see like what works for them, right? Maybe you tweak this around and you try different moving averages and see like what works for your plasma cutter, right? Because I know it works for my plasma table on my plasma cutter, but for you it might be different, right? So if you have enough people build these things and see like what works and come up with different plans, then we can all share those and help more and more people make their plasma cutters even better. But I think that's all on the Arduino side for now. So the next video is going to be digging into the very basics of HAL, the hardware abstraction layer in LinuxCNC. And then we'll build upon that in a series of maybe 3, 4, or 5 videos. And then by the end of that, you should have a plasma cutter with torch height control, ohmic sensing, like the laser diode that I have for zeroing stuff out, and all the other goodies you could possibly want, and be confident enough in doing that that you can customize your machine to how you want it. Especially with HAL. Oh my god, there are some good resources there, like the manual and documentation and all that is pretty good, but it's also very thick. And the majority of the advice you see on LinuxCNC HAL is just like copy and paste and pray it works. And that's not. Maybe you can make it work that way, but that's not the ideal way, right? I'm trying to teach you here to really understand what's going on, at least giving you the gist of it. So if you squint at it long enough, you can figure it out. And then from there, you can work out and expand it to be exactly what you want, because that really is the power of Linux, right? You can make it do whatever the fuck you want. You're not tied into whatever options your CNC vendor gave you. You can do whatever you want. It just takes some work. But it's worth it, in my humble opinion. Anyway, catch you in the next video.